staring in your face should trigger your memory banks, because you need to make a carboxylic acid somehow. There's no carboxylic acid in your starting material, so it should allow you to think in terms of that being the extra carbon that you add to the 2 carbon fragments, meaning that retrosynthetically at this stage, and there are many, many solutions to this problem, by the way, okay, to assemble this guy. So I'm just picking one. One possibility that seems attractive is to do this retrosynthetically, because we know that we can turn this into a Grignard reagent, and the Grignard reacts with CO2, and that introduces the missing carbon, the 5th carbon. Okay? So that would be a perfect way of doing it. You could do it also with cyanide, do an SN2 reaction with cyanide and then hydrolyze the cyanide. That also would give you that. So there are various ways of doing it. If you do the Grignard, bear in mind that there is a little trick you have to apply, because you can't make a Grignard in the presence of an alcohol. So you have to protect the alcohol as a tertiary butyl ether. Okay? So there's an extra step. This would have to be treated with tertiary butyl alcohol and acid. That makes the T-butyl ether. And the T-butyl ether is taken off with aqueous acid. Okay? That's the deprotection. So to make the Grignard and make the carboxylic acid, you would have to do it on the tertiary butyl ether. But otherwise, you're all set. So how do we simplify that? How do we get the bromine in there? Starting from a hydrocarbon, that doesn't look good, because hydrocarbon has, or hydrocarbon chain, I should say, has 3 different secondary CH2s, so radical halogenation of that wouldn't do you any good. One way to do this, and there are many ways to do it, I'm just picking one, would be to retrosynthetically go now to that, the terminal alkene. Okay? And the reason I like the double bond is because now I'm starting to think about what I have as starting material, and there's one species there with a double bond. But there are other options. Okay? You need the terminal double bond, because only that guy on Markovnikov hydrobromination will give you the bromine in the right place. Okay? If you put the double bond here, then HBr addition, unsymmetrical alkene, you get a mixture. Okay? And now staring at this guy, it should be completely obvious what we have to do, because this is the 4-carbon piece that is directly available from these 2 starting materials, namely by retrosynthetic cleavage here, which is that plus that Grignard. Okay? That Grignard does an SN2, opens the oxocyclopropane, and gives you the hydroxyethyl piece. That is what's required. Again, there are many other solutions. Okay? I'm just giving you one, and I urge you to try something else. Okay? This is such a general piece up here. You can put this together in many, many different ways. And you could try using other starting materials just for practice. All right, so let's go through the 4 classes one by one and see what they do. And we'll start as usual with the usual rhythm. Naming acyl halides are pretty straightforward. It's you turn the name alkanoic acid into alkanoyl halide. We've already done that, actually, repeatedly, starting with Friedel-Crafts acylation. So this one here, for example, is butane based. It's a butanoyl bromide, and at position 3 is a methyl, so this is 3-methyl butanoyl bromide. In cycloalkanes, we turn the cyclic naming of carboxylic acids, namely cycloalkane carboxylic acid, we turn it into carbonyl halide. So this is cyclohexane carbonyl fluoride, and carbonyl bromide, and carbonyl chloride, and so forth. Okay? That's very similar to other cyclic alkane type nomenclatures of other functions. So what are the reactions? This is repeat, but now I'm just focusing on acyl halides. Okay? And I'm driving home the point that acyl halides are really tops in terms of starting materials for all other carboxylic acid derivatives. The first one is just hydrolysis. We saw this before. That gives the carboxylic acid. And so the mechanism, water is deemed to be sufficient, acyl halides are deemed sufficiently electrophilic that you don't need catalysis, although it's very difficult to exclude proton. So you can write proton catalyzed. If you don't want to, you don't have to. Water can attack directly, kicks out the electron pair comes back in, kicks out chloride. And then you wind up with a protonated carboxylic acid that loses the proton. And you're done. Okay? In, out. So this example, these are quantitative reactions. And they're exothermic, so you have to cool often if you have a large batch. Alcohols, we treat them as alkylated water. They react like water, but now in this case they make ester. So an alcohol with ROH makes the ester. Operationally, frequently organic chemists add a base, and that is typically a tertiary amine, to mop up the HCl as the ammonium chloride. Or you add pyridine, which is a mild base also. In other words, or carbonate for that matter. Any base that mild base that might mop up the HCl, simply because if you have a more complex molecule, such as the one we just unraveled here, by the way, for example, you don't want HCl floating around here, okay? Because you have an OH sitting there. HCl may make the chloride and may make ether, whatever. It will cause trouble. So operationally, often the people add a base. You don't have to worry about that. So don't forget that when you use your schemes. That plus that gives you an ester. Remember, that guy comes with the carboxylic acid, so this is a good way of making, quantitatively, turning a carboxylic acid into an ester without worrying about the equilibrium that we would get if we mix the carboxylic acid with the alcohol that we discussed on Tuesday, which sets up the equilibrium. Okay? So this is the roundabout, quick way of turning a carboxylic acid 100% into the ester. So here's an example. This cyclobutane carbonyl fluoride with methanol. This is triethylamine was used in this case to mop up the HCl. You don't have to worry about that. That plus that gives the ester. Okay? Amines, same thing. Addition elimination. This is a great way of making amides. Remember, making amides from carboxylic acids and amines, big problem because you get the ammonium carboxylates, and then you have to heat the living daylight out of the system to get the amine to do the nucleophilic addition elimination. Here, no problem. Okay? So this works for ammonia, for primary and secondary amines. Tertiary amines, of course, they just add and come back off because there's no proton to be lost. So using methylamine, operationally, they actually use the reagent also as the base to mop up the HCl. So basically, they use excess amine, and you get the corresponding amide. And the mechanism is straightforward, it's additional elimination. So this guy comes in, pick out the electron pair, the electron pair comes back in, pick out chloride, you get the protonate amide, you lose the proton, and you're there. So they're all the same, these mechanisms. I hope I'm not starting to bore you. All right, so now we have something slightly new. After we've done now making carboxylic acids, we can make the esters, and we can anhydrides, esters, and amides. What about carbon-carbon bond formation? Now that we're discussing alkanoid halides, right? We have a very reactive carbonyl carbon. Can we use carbon nucleophiles to do addition elimination? That would be something new, and that would make a carbon-carbon bond the essence of organic synthesis. And the answer is yes. Now, your first solution to this, before I'm giving you the answer that's up here, would be to use an alkylithium or Grignard reagent. Right? They have nucleophilic carbon. We've used them since chapter 8 to make alcohols by addition to the carbonyl function of aldehydes and ketones. So this should work here too. And the answer is yes, it does, actually. Grignards will add additional elimination and make this product in this particular case if you use a propyl Grignard. So there's a propyl group here and there's a butyl that's from the urine. But the product, of course, also reacts with Grignards and alkylithiums. So you have a problem that the product competes with your starting material for the Grignard reagent, even though the product is slightly less reactive carbonyl than the acyl halide. So that's an inherent limitation which one can play with by low temperatures and things like that, but it's not satisfactory. A much easier way to deal with this is to use a modified organometallic that is much less reactive. So you modify the reactivity of the reagent rather than deal with the differential in reactivity between this carbonyl and that. And that reagent is cuprates. So this is the second use of cuprates. We use cuprates before to do conjugate additions to alpha-beta unsaturated carbonyls. You may remember that. And there you use the reduced reactivity of cuprates plus the fact that they can act as electron transfer agents to ensure beta attack rather than attack at the carbonyl function. Here we are doing attack at the carbonyl function, and these guys do not react with aldehydes and ketones. Okay. Already implicit in our prior application of conjugate addition to an alpha-beta unsaturated aldehyde and ketone, the product of those conjugate additions did not react with the cuprate. So that's why these are really good. So they do additional elimination. The R minus comes in, picks out the electron pair, comes back, pick out chloride, out comes this. Okay. So there's one example. Here's a more complex example. It works quite well, 70% for an unsaturated cuprate, okay, which is a bunch of methyl groups, for this cyclohexane carbonyl chloride to make the alpha, in this case, an alpha-beta unsaturated carbonyl. The reason, then this guy is stable in the presence of this because this is much more reactive than the product here. Okay. So cuprate will attack the carbonyl halide before it attacks any piece of this. Now, where there is organometallic additions, we started doing this in Chapter 8, we always discuss also the corresponding hydride reductions. Okay. In Chapter 8, we introduced sodium borohydride and lithium aluminum hydride as hydride-reducing agents, and they would take the carbonyl to the alcohol. So now the question is, can we do this with acyl halides? And if this works, in principle, one ought to be able to displace chloride by H-. That would be a new aldehyde synthesis, turning acyl halides into aldehydes, meaning that since acyl halides are derived from carboxylic acids, you would have a way of converting a carboxylic acid into an aldehyde directly. Okay. Well, you can't do this, obviously, with sodium borohydride and lithium aluminum hydride because the product that you want is an aldehyde. And we already learned in Chapter 8 that sodium borohydride and lithium aluminum hydride reacts with aldehyde. So all this will do is take the acyl halide all the way to the alcohol. So you don't want that. So here again, you modify your reagent to become less reactive, less hydridic. And the way this is done is to invent this reagent here, in which lithium aluminum hydride, which I call the atomic bomb, is basically reduced to the power of a firecracker by reacting it with 3 molecules of tertiary butyl alcohol, okay, which react with the H- here. This H+ reacts with the H-, and you introduce 3 alkoxy groups. This is this beast here, but it's basically 3 tertiary butoxy groups. 1 hydride is still left. Okay. Now, if you make a model of this, it's a little hydride sitting there on the aluminum, surrounded by this garment of tertiary butoxy groups, and it's highly sterically protected and less hydridic than in the original lithium aluminum hydride. And that guy turns out to be unreactive in the presence of aldehydes and ketones. It's just too hindered and not hot enough as a hydride transfer agent. And therefore, but it will react with the more reactive acyl halides. And so you can take that plus this modified hydride, and out comes the aldehyde. And here's again a rather complex system, an enoyl halide to show you that even alpha-beta unsaturated systems work well, and you get the corresponding aldehyde. So that 2 new pieces of vocabulary, you can turn alkanoid halides into ketones by cuprate addition and into aldehydes by the corresponding hydride addition chemistry. So much for acyl halides. Let's briefly look at anhydrides and then call it quits. Anhydrides, I won't ask you to remember nomenclature, but basically you already see what happens. You just take the carboxylic acid name, the alkanoic acid name, and you displace acid by anhydride. Okay? The symmetrical anhydrides are obviously the ones that everybody uses, because if you have an unsymmetrical system, then the 2 carbonyl functions are different, and you get mixtures of products, so that's not good. Cyclic systems are used, and there's a nice application of this that I'll show you in a minute. But overall, they react like acyl halides. Okay? So water will hydrolyze them. Alcohols makes the ester. The leaving group, of course, leaves as carboxylate anion. Here it's protonated, so both parts make the carboxylic acid. With alcohol, one part, the acyl part, turns into the ester, and the other part makes the carboxylic acid. Okay? And that's one of the inherent limitations of using anhydrides in organic synthesis. You basically waste half of the reagent. And that's, in terms of green chemistry, not desirable, because green chemistry asks you to use all carbons in your starting materials, have them be incorporated, if you can, have them be incorporated in your product, because there's less waste. Okay? Amines make amides, but again, you're wasting one as a side product, the carboxylic acid. In industry, you recycle it, but that's cumbersome. Now, there's one, okay, so then mechanistically, this goes again by addition elimination, so there's nothing new here. Addition, get the electron pair out, it comes back in, you pick out as a leaving group now carboxylate anion. The carboxylate anion, of course, is basic. The product is protonated in the initial stage, so the proton jumps from one to the other, and you get the product plus the carboxylic acid. But of course, everything is worked up with acidic water anyway, so everything is protonated. So here's an example. Acetic anhydride hydrolyzes 100% to this, but if you take methanol, you get the corresponding ester plus 1 molecule of the carboxylic acid. And because you're wasting part of the reagent, this is not very popular. There's one application, however, where it's actually unique, and you have to use an anhydride, and that is cyclic anhydrides. Cyclic anhydrides solve one problem of regioselective functionalization of a dicarboxylic acid. Let's assume you have this dioic acid and you want to selectively functionalize only one carbonyl function. That's very hard to do because there are two of them in the molecule, and any nucleophilic reagent will attack either one randomly. Okay? So the trick is to turn this dioic acid into the corresponding anhydride. And you do this under mild conditions with thionyl chloride, because as soon as one thionyl chloride has turned one carboxy function into the corresponding acyl chloride, that acyl chloride will be attacked by that oxygen by addition and elimination, along the mechanisms we did here for the carboxylic acid anhydride formation. So instantly you get this. Alternatively, you just heat it. Okay? Remember, if there's no other functionality around, these are very stable thermally. You can heat them to 250 degrees. They blow out water by, again, this mechanism here. Or you can use acid catalysis. Anyway, you can make the anhydride. And at this stage now, you can attack the anhydride with a nucleophile. I'm picking amine as a potential nucleophile. And you do the addition elimination. And now, of course, the leaving group stays attached to the product because it's a cyclic system. So you have this beautiful desymmetrization of the original carboxylic acid, where one function has turned into an amide, and the other function stays the carboxylic acid. So that's one very useful application of anhydrides. The other one is Friedel-Crafts reactivity. We mentioned this in the Friedel-Crafts section, and we bypassed anhydrides, but they, of course, act as acyl cation equivalents, and this goes by the classical mechanism. So aluminum chloride attacks first kinetically that oxygen to make this resonance-stabilized intermediate, but that's not actually the one from which you can rip off the carboxylate group to generate the acylium cation. Remember, in the Friedel-Crafts acylation, you go through the acyl cation, which is also resonance-stabilized. So this is really a dead-end intermediate. It goes back, and every now and then the aluminum jumps to the other oxygen, which is the OH oxygen. So here we have a case where, indeed, it's the OH that is active. Aluminum goes here, turns it into a leaving group, and or the OR in this case, O-carboxylate, and it rips it off, and you make the acyl cation that way. Remember, in the classical Friedel-Crafts acylation with acyl chloride, this was a chlorine that got ripped off by the aluminum chloride. Here we're ripping off the carboxylate, but the process is identical otherwise, and then you go into the mechanism of acyl cation additions. And again, if you use a cyclic anhydride in these transformations, you do the electrophilic acylation, but again, the leaving group now, this piece, doesn't come off. It stays attached. So there again, we have a way to desymmetrize dioic acid through the anhydride in Friedel-Crafts chemistry, leaving one end as the carboxylic acid, the other end becomes a ketone. So anhydrides are very useful for synthetic purposes for that reason. And that's where we'll leave it today. Have a nice weekend.